Okay, here we are for AP Physics, Simple Harmonic Motion. Going to take a look at problem number 7. Problem 7 says, the amplitude of a system moving in simple harmonic motion is doubled. What would be the change in total energy, the maximum speed, the maximum acceleration, and the period if we double the amplitude? Alrighty, so here we go. I'm going to work that separate paper, of course. All right. Okay. We're going to double the amplitude. Okay. We want to know first what happens to the total energy. And so you say, well, what I'll do is I'll make use of the fact that when I have something in simple harmonic motion, that when it's at its amplitude, all of the energy is in potential energy, right? And we know that for simple harmonic motion, we know the force has to be proportional to x, to the displacement from equilibrium. And since force is du dx, negative du dx, right? If I rearrange this, right, I could say that integral f dx, right? You know what I mean? Remember that the opposite of the work done by that force is equal to the change in potential energy, right? That's associated with that force, right? And so you say to yourself, well, gosh, then, basically to get the potential energy function, I want to integrate this, which means the potential energy function is going to be, with respect to x, if it's proportional to x, when I integrate, you say, hey, that energy is proportional to x squared. Now, what I'm going to do is I'm going to double the amplitude. The amplitude is the maximum displacement when I'll have maximum potential energy. I'm going to double it, but it's squared. So if I go and I double that maximum displacement, and then I square it to get the potential energy, you see, I can recognize that doubling it is going to make it 4 times bigger. So my new E total is 4 times the old V total. All right, part B. Part B says, hey, what's going to happen to the maximum speed? Well, I know that I'm going to have maximum speed when I'm at the equilibrium position. At the equilibrium position, the potential energy is 0, and so all the energy is in kinetic. So in other words, I know that my K max, kinetic energy maximum, is equal to my potential energy maximum, right? And since we just, the new energy is 4 times, right? The maximum kinetic is 4 times. So you say, well, kinetic energy is 1/2 mv squared. Say that's the old kinetic energy. Now I know that the energy is 4 times as much. So it's like I'm going to take this function and I'm going to make it 4 times bigger. But I'm not changing the mass. This v squared has to be 4 times bigger. The v is being squared, so it's got to be double the speed. So the new v max is 2 times the old v max. Okay, make sense? Okay. Which takes us to part C. They'd like to know what doubling the amplitude would do to the maximum acceleration. And you say, well, here's what I know. I know that force is proportional to the displacement again, by definition of a simple harmonic oscillator. I'm doubling the max, I'm doubling, and I know that when I'm at the amplitude, at the maximum position, that's when I have the maximum force. And since F is ma, that's when I have the max acceleration. It's when I have the max force. And you say, if I double the force, I would double the ma, but the mass isn't changed. I'd be doubling the a, right? What's going to happen is we're going to double the distance we pulled from equilibrium, and so that's going to double the force, so it'll be double the acceleration. Does that make sense? I hope that makes sense, right? I'd be doubling that, I'd be doubling that, which means doubling that, right? So I know that my new maximum acceleration will be 2 times the old max acceleration. Okay, which takes us to part D, okay, which asks about the period. And you say, well, I know that t is 2 pi root m over k. We did not change the mass of this oscillator. We didn't change the spring constant. Now, again, technically, this isn't necessarily a mass on a spring. But the point that I'm getting at here is that the period depends on just these physical quantities of the system. It doesn't depend on how far you've stretched the system. Remember, one of the things that makes simple harmonic motion so cool is the fact that the period is constant, regardless of how far you displace the system from equilibrium. So the period is not affected. It's the same as the old period. It's not affected by amplitude. All right, that's problem 7.